Dear students, in this lecture we are going to discuss about the fundamental aspects of the mechanics of solids. We will discuss about the stress, strain and their relationship, and also we will discuss about the stress strain diagram for a ductile material. In the engineering field we encounter the machine components subjected to external forces, and because of these external forces sometimes these machine components tend to get deformed, or even if their values are sufficient enough, these forces may break these components apart. Therefore, the knowledge of how the components will behave under the action of these external forces is very important for an engineer. These external forces which acts on the rigid body are generally termed as loads. Here in this figure you can see that a component is subjected to the external forces or the loads of the magnitude P. When a body is subjected to external load, it undergoes deformation, and the molecules of the body resist this deformation. So the internal resisting forces are set up with the application of the external loads. If we draw a free body diagram of the cut section of this particular part at the cross section XX, we can see on the left hand side there is a force of magnitude P is acting. On the right hand side, to balance it, there are internal resisting forces which will be distributed over the entire area are shown over here. Now the magnitude of these resistance to the deformation can be termed as stress, and its value is given by the applied load divided by the area of cross section on which it is being applied. So stress, which is represented by sigma, is nothing but applied load divided by the cross section area of the body. So applied load as is given in Newton and the cross section area is in meter square, so the stress value will be in Newton per meter square. So we can define the stress sigma as the resistance offered by the body to the deformation. There are two primary type of stresses or basic type of stresses. The first one is called as non-normal stress, and the second one is called as shear stress. Normal stress is the stress which acts normal to the stressed surface or the cross section area. As in the previous case I have shown here, this is the normal stress because it was acting perpendicular to the area on which it is being applied. The other stress is termed as shear stress. These stresses act tangential to the stress surfaces. Now these normal stresses are of two kinds. One is termed as tensile stress, the another one is called as compressive stress. Now what is the tensile stress? So a tensile stress is the stress when two equal and opposite collinear forces pulls the body in such a way that they tend to increase its length. Like in this figure you can see that the component which is being subjected to two opposite forces of magnitude P which are applied axially, and these forces are trying to pull the body such that they are trying to increase its length. So such type of stresses which will be induced in this component will be termed as tensile stress. They are represented by the symbol sigma T. Sigma is the stress symbol and T is a subscript which is used for tensile stress. We consider these stresses as positive stresses. So whenever the length of the component is being increased because of the application of stresses, we will term it as tensile stress and we'll call it as a positive stress. Now the second type of stress, which is another normal stress, because again here the stress produced are perpendicular to the area on which it is being applied, are termed as compressive stress. Compressive stress are produced when two equal and opposite collinear forces pushes the body and tends to decrease its length. So mind it, here again there are equal and opposite forces, but they are acting in such a manner that they are pushing the body and they are tending to decrease its length of the body. So this induced stress are called as compressive stress, and it is represented by sigma c. C is subscript for compressive stress. These stresses are considered as negative stresses. Now there is a term which is related to this stress, is termed as strain. We know that when we apply the external load, the stress will be induced in the body, and because of it, applied load, the body's external dimensions will get changed. So the body which is subjected to external forces will undergo the deformation, and the measure of this deformation can be given as change in length of the body divided by the original length of the body, and it is known as strain. So strain is represented by symbol epsilon, it is the Greek symbol, and as it is a change in length of the body divided by the original length of the body, so this is a dimensionless quantity. After discussing normal stress, now let's talk about the shear stress. Shear stress is the stress which will be produced in the body when the two parts of the body exert equal and opposite forces on each other, laterally in a direction tangential to their surface in contact. You can understand this with the example of this rivet and plate system. You can see that there are two plates here which are joined with the help of a rivet. So when these two plates are being pulled in different direction, opposite direction, then because of it, this rivet may fail at the middle of it, at this juncture. So this is the diagram of the rivet failure here. Because the applied load are acting tangential to the cross-section area of this rivet, so therefore the stresses which will be produced in this rivet will be of shear stress. It will be represented by the symbol tau, and its magnitude will be given by the applied force divided by the cross-section area. Again, because of it, its unit will be Newton per meter square. So in contrast to the normal stress, shear stress acts tangential to the surface or tangential to the resisting surface. Now let's talk about the stress strain curve for the ductile material. I hope you know that what is a ductile material. A simple definition of a ductile material is the material which can be drawn into the shape of wire by the application of tensile load. So a material which can be easily drawn into wire or whose cross-section area can be reduced continuously without failure are termed as ductile material. In contrast to them, there are brittle materials which, when are subjected to such kind of forces, will tend to break down or fails. The example of ductile material are like aluminium, mild steel, and many other such materials. So in order to get this stress strain curve, we need a tensile test machine. A tensile test machine is a very simple machine which are having a kind of jaws at the top and bottom, and we put up a specimen of the material which we want to test in these jaws. Machine has an arrangement by which it can pull these jaws apart and thus subject this specimen to a tensile load. There is a arrangement available there which measures the amount of load that is being applied, and then there is also arrangement by which we can measure the change in the length of the specimen. One such specimen is shown here in this figure, and there is a middle cylindrical portion of this specimen, and length of it is measured at before the start of the experiment. So this length L0 or LO is termed as gauge length. We also measure the cross-section area of this specimen before the start of the experiment. So thus we know that value of initial cross-section area. Now when this specimen is put up in the tensile test machine and the force or the external load is being applied and its both ends are being pulled apart, we keep on measuring the change in the length of the specimen along with the value of the load that is being applied. When we plot the stress which is being produced in the specimen on the y-axis, which is nothing but the load, instantaneous load value divided by the cross-section area, the original cross-section area that we have measured before the start of the experiment, against the strain on the x-axis, which is nothing but the deformation that is produced in the specimen divided by the original length measured at the start of the experiment. So this is a curve of stress strain between stress strain for a ductile material. Some salient point or which occur in this stress strain curve are written down over here. We can see point P, point E, point Y dash, point U and point F marked on this graph. Now there is a importance associated with each of these points. Let's first talk about the E point, which is the elastic limit point. So elastic limit point is the point where, or up to that point, if we remove the load, the component will return back to its original position. So that means each time anywhere before the point E here, if we remove the load, our component will follow the line and return back to the original position. So there will not be any residual deformation left after the removal of load. So a property of the material which is associated with this elastic point, which is termed as elasticity, it is the property of material to revert back to its original position on the removal of loads. Beyond the point E, if we applied more load, then the component will not be able to return back to its original shape. There will be some residual deformation left in the component. So we are not going to follow the line back to the origin O here. Rather, we will follow a line which will be parallel to it. Suppose we go beyond the point E, and let's say somewhere we are between point E and Y. So there will be a line which will be parallel to P and original straight line, and there will be some residual deformation which will be left here. So this is the residual deformation which will be left here. This will be called as permanent strain. Now the another point that we can see on it is point Y, which is termed as yield point. So yield point is the point where there is appreciable deformation without further increase in the load. We can see here in this that there is a continuous elongation of the component while we are not actually increasing any load here. So such point is called as yield point. So yield point is marked with the increase in the deformation without further increase in the load. Y is the upper yield point, while on the other side y dash is called as the lower yield point. So after lower yield point, again if we want to deform the material, we need to increase the value of load. So we can see here again the value of the load is increasing up to the point U. U is termed as ultimate point. At the point U, it is the maximum deformation, the maximum stress the component can be subjected without failure. So after U, there is a phenomena that is called as necking that happens, and there is a local reduction in the area of the specimen. So here is our specimen. At the somewhere at the middle of it, we will see that local reduction of the area will take place. Before that, the reduction in the area is taking place during the entire process, but it is comparatively uniform. But after point U, because of this local reduction in the area, which is termed as necking, it will cause a very high reduction in the area at the middle. Now, after point U, there will be a point where the component will fail, and that point is given by point F, or the fracture point. It appears from the figure that the amount of load that is needed, or the stress value that is needed to fail the component, is lower than the ultimate point, while it is not true, because the simple reason is that there is a localized reduction in the area, and while drawing the value of the stress, or deriving the value of stress, we are using the original area. So this graph which I have shown in the red here in the stress strain curve is based on the area which is measured before the start of the experiment. If by some means we can measure the actual area, which is actually far less because of the application of the load, then if we draw that stress value, the value of the fracture point will be higher than the point U, as shown here. So this curve which is in dashed, it is based on the actual area of the component when it is being subjected to load. Now let's talk about the point P, which is occurring before the point E, which is the elastic limit. So point P is called as proportional limit. Up to the point P, the stress strain curve is a perfect straight line. After point P and between point E, this curve is no more a straight line. Usually for most of the material, the ductile material, the difference between point P and point E is not much. In fact, for all practical purposes, they are taken as one. So point P is the point up to which point the stress is proportional to strain, and we get a perfect straight line in the stress strain diagram. So because stress is proportional to strain, it is shown here in this equation form, and this is termed as Hooke's law. So according to Hooke's law, in this initial phase of the loading, the stress remains proportional to strain. Now we can change this proportionality with the help of this equality sign by using a Young's modulus or constant here. This is termed as E, capital E, or sometimes it is also called as modulus of elasticity. Its unit will be Newton per meter square, and using this we can write our first equation, that stress over strain is equal to value E, which is Young's modulus or modulus of elasticity. I have already defined you the strain, which is given by epsilon, and it is given by delta L by L, change in the length of the body divided by the original length. And we have also defined the stress for this tensile case as P by A, applied load, divided by the cross-section area of the body. Using this equation 2 and 3 in equation 1, we can get this equation delta L is equal to P into L divided by A into E. So delta L is the change in the length of the body. We can see this change in the length of the body is directly proportional to the applied load P, the original length of the body L, and it is inversely proportional to the cross-section area and the Young's modulus of the body. We have made certain assumptions while deriving this relation. We have assumed that the load must be applied perfectly axial to the center of gravity of the body or geometric center of the body, and the material must be homogeneous throughout. The body should be of constant cross section. If it is circular, it should be constant circular at all the point, and if it is a square or rectangle, it should be like that for the entire length of the body. Then we have also said that the proportional limit is not exceeded because we have used the Hooke's law in deriving this equation. So that is all for the today's lecture. We will cover more aspects of this, fundamental aspects of the mechanics of solid in next lecture.